Hi everyone, my name is Nika, and in this session, we continue exploring neural networks. Today's topic is optimizers. There are different ways to optimize neural networks. Some optimizers reach the minimum error faster, while others take more steps to achieve the same result. In this lesson, we'll explore common optimizers available in the Keras library, discuss their key features, and compare their advantages and disadvantages. We'll then move on to the practical task for this session. We'll generate a small dataset with x values, define a simple function, and create target values based on that function. This function will act as the true law our neural network will try to learn. We generate 50 data points between -2 and 2.5. To ensure reproducibility, we set a fixed random seed, so every time we run the code, we get the same training points. We then pass these x values through a predefined function, our true law, and add a small amount of noise to the outputs. This simulates real-world data, which is often noisy. After generating the data, we visualize it. The blue dots represent the training points that will be used to train the neural network. The neural network we use is intentionally very simple, just a single neuron, because the goal isn't to build a complex model, but to examine how different optimizers affect learning. We initialize the network's weights manually and make an initial prediction across all data points. Of course, the initial weights don't fit the data well, but we can already visualize the predictions and compare them to the ground truth. We then define the mean squared error MSE as our loss function, since we're solving a regression task. MSE will measure how close our predicted values are to the true outputs, and will help guide the optimizer toward better weights. We mark the starting point of our optimization initial weights in red. Our goal is to find the point on the surface where MSE is minimal, ideally close to zero, indicating our model's predictions are very close to the actual data. To achieve this, we'll use gradient descent, an optimization algorithm that was already introduced on this channel. If you haven't seen that video, it's linked in the description and in the previous tips. Now, let's move on to implementing a gradient calculation function for the MSE loss. We'll revisit the MSE formula and derive its gradients with respect to both weights, which we'll use to update the model during training. Now, let's break down how we actually compute the gradient and implement gradient descent step by step. We begin by expressing the prediction function directly using our coefficients. We multiply the input x by weight w1 and add the bias term w0. Since the loss function is MSE, which is the squared difference between the prediction and the actual value, we then calculate that difference, square it, and average the results across all samples. To optimize the model, we need to find the partial derivatives of the MSE with respect to each of the weights. These gradients will tell us in which direction to update the weights to minimize the error. Now we're ready to implement gradient descent. First, we initialize the weights with some starting values. These weights will be adjusted over time to reduce the error. Then, we run a loop for a fixed number of iterations. 1. On each iteration, we calculate the gradient. 2. Multiply it by a learning rate. We choose 0.1 to avoid overly large or small updates. 3. Subtract the scaled gradient from the current weights. 4. Save each updated weight into a list so we can track their evolution over time. Additionally, we include an early stopping condition. If the weights don't change significantly between iterations or stop changing altogether, we exit the loop early since the model is no longer improving. We start with an initial bias, for example, -9, and an initial weight, say, 0.5, and after running gradient descent, we might end up with final weights like W0 equals 1.99 and W1 equals 0.01. Using these final weights, we generate predictions by plugging them into our model, and we visualize the results. The new prediction line closely follows the original function, even though we added some noise to the data. This shows that our simple neural network, optimized with gradient descent, has successfully learned the underlying pattern. Finally, we revisit our 3D error surface and plot the entire training trajectory, from the initial high error weights to the final low error ones. The path looks smooth and clearly shows how gradient descent steadily reduced the error. But there's one drawback we must acknowledge. Basic gradient descent calculates the gradient using the entire dataset at each step. While this may work for small datasets, it becomes computationally expensive for large datasets, potentially exceeding your memory capacity. If the dataset is too large to fit in memory, this method becomes infeasible. However, that doesn't mean we give up. The solution is to use a more efficient variation of gradient descent, such as stochastic gradient descent (SGD), which uses one data point at a time, or mini-batch gradient descent, which uses small subsets of the data. These alternatives allow us to train on large datasets efficiently and continue improving our models. Now let's talk about stochastic gradient descent (SGD) and how it differs from regular gradient descent. The key difference lies in how much data is used at each training step. In regular gradient descent, we calculate the gradient using the entire dataset. But in stochastic gradient descent, we update the model based on just one randomly chosen data point at a time. Here's how it works. During each training iteration, we randomly select a single data point from our training set. We then compute the gradient of the loss function using only that one data point. This gradient tells us how to update the weights so the error on that one point gets smaller. We scale the gradient by the learning rate, just like before, and subtract it from the current weights to get the new ones. This approach has a major advantage. Since we only need to load one sample at a time, we avoid memory issues, even with very large datasets. We're no longer trying to fit the entire dataset into memory for each step. We implement this version similarly to regular gradient descent. We initialize the weights and keep track of how they change over time. At each step, we randomly select one training sample and compute the gradient only on that point. We apply the weight updates and record the new weights. After training, we can visualize how the weights have changed. Even though we trained only on one example at a time, our final predictions are very close to the true target function. The orange prediction points align well with the ideal curve, despite the noise in the training data. Yes, the optimization path using SGD is a bit more chaotic. The updates don't follow as smooth a path as with full gradient descent, but we still converge to a low error solution. And here's the big win. Stochastic gradient descent is much faster than standard gradient descent, especially when working with large datasets. While batch gradient descent needs to compute gradients over the whole dataset at each step, SGD only looks at one data point, making each iteration significantly faster. We can also visualize how SGD affects the loss surface. Due to the randomness in sample selection, the error surface appears more jagged and the path is less smooth. But in the end, the model still reaches a low error region, just like with standard gradient descent. So, while SGD introduces some noise into the learning process, it allows us to train faster and more efficiently, and is often the better choice for large-scale machine learning problems. Another variation of gradient descent is called mini-batch stochastic gradient descent. In this method, training doesn't happen on a single random data point as in pure stochastic gradient descent, nor on the entire dataset as in classic batch gradient descent, but on a small randomly selected batch of data points, typically 10, 20, or more. The exact batch size is up to you and depends on your preference and system capacity. In mini-batch SGD, we train on a small number of randomly chosen examples in each iteration. The weight update steps remain the same in principle. We calculate the loss error, compute gradients, and update weights accordingly. Assume we use a batch of 10 objects with initial weights. For each training step, we randomly select 10 different samples without repetition, compute the error and gradient based on these samples, and then update the weights. Over iterations, we see how the weights change. When we visualize predictions, the result looks quite good. The prediction line passes nicely through the data, although it slightly deviates near the end. Still, it's one of the best fits among the methods. In mini-batch SGD, the loss curve doesn't follow a perfectly smooth path like in batch gradient descent, but it also isn't as erratic as in pure stochastic gradient descent. Instead, it's semi-random and more stable, offering a good trade-off between noise and computational efficiency. Today ends our video. Thanks for watching, and good luck as you continue learning deep learning.